Good afternoon, everyone, and welcome to the second Art Meets Science at SLAC lecture. I'm Angela Anderson with the Office of Communications at SLAC, and I'm very pleased today to welcome to stage both an artist and a scientist to converse about the ways that art and science have influenced and inspired them, but also to share with you a very special and beautiful collaboration that came about during their first meeting at SLAC last October. The artist is Nitin Sawhney. He was just awarded a CBE in the Queen's New Year's Honors List, and he's one of the most distinctive and versatile musical voices around today. He has achieved an international reputation across every possible creative medium with over 20 studio albums to his name, including solo albums, film soundtracks and compilations, as well as 50 scores for film and gaming. He is the recipient of many notable national and international awards, including the Ivor Novello Lifetime Achievement Award in 2017. Most recently, he completed the entire composition of Netflix Warner's Mowgli, Legend of the Jungle, directed by Andy Serkis. Nitin is the inaugural artist of Stanford's presidential residency on the future of the arts, and I want to thank Stanford Live for bringing Nitin to SLAC as a part of this residency. Nitin will be joined by our own Risa Wechsler. She is the director of the Kavli Institute for Particle Astrophysics and Cosmology, which is a joint institute between SLAC and Stanford University. She is an associate professor of physics at Stanford and of particle physics and astrophysics at SLAC, and she joined KIPAC in 2006. Her work combines numerical simulations and modeling with some of the largest existing and future galaxy surveys, which are mapping the universe to learn about the nature of dark matter and dark energy. So please join me in welcoming Nitin Sawhney and Risa Wechsler.
Thank you. That was beautiful to see.
It is. I mean, it's interesting because the first time I saw this was when you were talking about it here.
Right.
And I mean, it was so gorgeous because I saw it in 3D, and it was such a great visualization that I just thought it was bizarre to me that there wasn't any music, and I kind of felt I was like, wow, it just felt like a great opportunity. So and it's so powerful to me and so profound to watch ionizing gas. I mean, do you want to tell us a bit about
Yeah, so let me just say a little bit about the science behind the movie that you just saw. So that movie was taking place in the first billion years of the universe. It's during a period of the universe called reionization. That's because what's happening during that period is the movie starts kind of right at the beginning of when the first galaxies start to form in the universe, just less than a billion years after the Big Bang. And when those first galaxies start to form, the universe is filled with hydrogen gas, and the energy from the stars in those galaxies actually ionizes the gas, basically clears it out. And that's what you saw in that movie, that the gas sort of went from being opaque in the beginning of the movie towards the end, at sort of after about a billion years. The gas has been cleared out by the generations of stars that form. And so it's not a very, in a cosmological time scale, for me, I work on the whole history of the universe, about 13.8 billion years. So for me, that's a short time period. For most of us in our daily lives, a billion years is a long time. One of the things you saw in that movie was that there's a lot of structure in the universe, so it's not perfectly smooth. So, the galaxies form in certain regions initially, and then, later the emptier regions clear out. I love watching it with, this movie is especially beautiful in 3D because it has so much depth to it. This movie is based on work done by my colleague Tom Abel and his group, and the visualization was done by Ralph Kaler, who's here at SLAC, and he's amazing at making these movies. He has a lot of work in planetariums here and in New York. So I think actually both of these movies have shown at the Cal Academy and in New York at the planetarium there. But I love seeing it with this music because it sort of just, it makes the wonder that you see when you watch it just so much more visceral.
Well, thank you. So originally, this piece of music this is one composition. There's going to be two compositions we're going to show, including this one. And the other one is a totally brand new composition, but this one was an adaptation from a piece that I'd written called Spirals. And I just felt it fitted really well. And actually, I played it outside just here in the I don't know what you call that area, but in that area outside. Last time I was here in October, but it just felt like it just really fitted, and the impact on me. I mean, it's very interesting because as an artist, I respond intuitively to what I see and what I feel, and it's fascinating to me that Albert Einstein once said it was. Shinichi Suzuki, who quoted him in 1969, saying that he once said that that relativity came to him through his musical intuition. And actually, Einstein was an amazing violinist and was the chair of the Princeton Orchestra. And he had conversations with a polymath from India called Rabindranath Tagore in 1927 and 1930 in Berlin. And in those conversations, they talked about the nature of music and the nature of reality, and they touched upon so many different ideas, from theology to physics to music to philosophy. And I just found it was such an interesting kind of, or those two conversations were so interesting in the juxtaposition of science and somebody who come from an artist background. And so for me, I've always been really interested in the idea of collaborating with science as an artist, as a musician.
Yeah, I mean, I just love the fact that putting the music to to this, I think brings it just so much more depth, and kind of just brings it, opens up, a different kind of appreciation of its beauty.
Yeah, I think it's kind of well. Thank you for saying that. But it was. I was very lucky to be joined on that piece of music, which is based on a time cycle of seven beats. It's in 7/8 time, and the musicians who I was joined by were Manu Delago, who plays with, I don't know if you know Bjork over here, but he's a fantastic, and he also plays with Anushka Shankar, who's a very good friend of mine, Panditji Ravi Shankar's daughter, and he's an incredible musician playing what's known as the handpan, and I really love the way he plays, and it just felt really appropriate, but also the incredible bansuri, which is an Indian bamboo flute played by Ashwin Srinivasan, who I also got to play on the music that I did for Mowgli, which is the Netflix film, and he just gives such depth to his expression, mainly in the way that there's such a fluid way in his musical articulation that's based in Indian classical rag. So yeah, I mean, I was very happy to be joined by those musicians, and they really, I think, enhanced the piece and how it worked. Hopefully, with the visuals, amazing.
Yeah, I mean, I think there's this movie in particular. There's such a richness to the way, it's interesting. We were talking earlier today about the interesting thing in cosmology, how you have to deal with such a vast range of time scales and length scales. And actually this movie, both of the movies you'll see, there's evolution in time and motion through space. And so, the span of the first movie is maybe 500 million years. The span of the second movie you'll see is closer to about 13 billion years. Right. But even in this period, you could see there was stuff happening, right? There was, this depth of the gas and the thickness of the gas was sort of clearing out over the time of the movie. And I think that sort of having the music sort of brings you into that a little bit more.
Well, that's cool. I was just wondering, as the person who actually created the simulation or visualization was Ralph Kahler, and I'm just I was asking you earlier about the way in which you generate the information that all of this is based on. So would you like to explain that again?
Sure. Yeah. So in these simulations. We start out with some understanding of what are the basic constituents of the universe. So how much of the universe is made of normal stuff like you and me, atoms basically, how much is made of dark matter, how clumpy is the universe, like how much stuff do you have clustered in big things versus small things. So there's basically 6 or 7 numbers that we use to describe all of those things, basically what the universe is made of, how clumpy it is, and how it's expanding over time. And actually in the second movie, which contains only gravity, those are the only numbers that go into that, plus gravity. In this movie, there's a little bit more in it, because what you see is that there's gas, and that there's also star formation. And that actually is much more complicated than gravity. Gravity is the easy part. And so what you saw in this movie was that there are actually galaxies forming. And those galaxies form out of the places where you have dense regions of matter. And then after they form, they eject this energy into their surroundings. And so that's sort of what is happening in the computer. And then Ralph takes those simulations and turns them into these really beautiful visualizations.
It's incredible. Actually, it's interesting listening to you talk about numbers as well, because Werner Heisenberg talked about the where he quoted Pythagoras, because Pythagoras originated ideas in terms of musical ratios and understanding the intervals within music, and that was developed on by Johannes Kepler and also Vincenzo Galilei. So they kind of took the ideas of ratios, but actually in Werner Heisenberg's concept of the universe, he talked about the perfect number being 10 because it was the sum total of the first four integers of that we use to generate ratios in music. And I kind of think it's always fascinated me with physicists who are able to kind of look at the nature of music and its place within cosmology and within understanding, harmonic resonance, and people like Tesla. And it's interesting how physics has really kind of had a very strong kind of relationship with the evolution of music.
Yeah.
And the way, I mean, for example, my guitar is only tuned the way it is because of Pythagoras. And so it's kind of it fascinates me that there is this kind of constant symbiotic relationship between science and music that continues over time.
Absolutely. What first got you interested in thinking about science and its relation to music?
Well, I think I've always been interested in science and maths since I was very small. But I mean, for example, we were talking earlier about fluidity of thought, and with music, I mean, I was classically trained as a pianist first, but I also played a number of different things. I got into playing flamenco guitar, and then I was a jazz pianist, and then I played tabla and sitar, and then I was in a punk band, a rock band, a funk band. So I kind of, and I was in an orchestra. So I was kind of, but I was always experimenting. And my whole thing was that I always thought of music as a place for patterns. We were talking about pattern recognition and finding relationships with different ways of thinking about music. So, for example, with the way in which music is taught, quite often within the classical world, it will be very much like a newsreader might read the news. Perfect kind of diction, and looking, well, in some places, and reading from an auto cue. But it's about great enunciation, but not necessarily understanding or being able to improvise around the subject that they're talking about. And so if you take away the auto cue, maybe they might struggle to explain what it exactly was that they were talking about just before. And but it's very precise in the way that they have been trained to explain. Whereas, for example, a stand-up comic will actually improvise around words and improvise around ideas. And so for me, that's the difference between a classical musician and jazz musician. So I kind of, I was always looking at how you become more fluid, and it was the same with mathematics. When I was very young, I got frustrated listening to people reciting times tables, which is what they did when I was growing up. I don't know how they teach maths now at schools, but they would be very much about reciting from memory as opposed to learning how to calculate. I never thought that was mathematics. And in the same way, I didn't really think that I was engaging with music until I started being playful. And I think it's, with all the scientists and with all the people that I've admired, whatever sphere of knowledge they come from, they're playful, and they actually like to look at a subject from many different angles. And so I think music and science from that point of view always felt very much coming from the same place to me.
Yeah, I think it's one thing that is so fun actually about physics, that we also have these very clear rules about how the universe works that we're trying to figure out, but there is a lot of play. And there's a lot of trying to understand how pieces fit together, trying to connect one thing to another thing to see how they might relate, and to see if you might learn about one thing from the rules that apply to another thing. I think I think one of the things that's great about sort of thinking about art and science and their connection is this similarity between sort of the interaction between rules and sort of creativity. And, we talked about, I was also a classically trained ballet dancer, which also has rules, but then a lot of playfulness and can have a lot of creativity as well.
That's right. I mean, it's interesting with that as well. I mean, I work a great deal with dance, and actually Akram Khan, who I work with a lot, came over here and was working with your, I think, cybernetics department. But he's very interesting that he comes from a discipline in India called Kathak dance, and Kathak dance is based on a treatise that was written 200 BC called the Natya Shastra, which looks at the vocabulary of lots of different disciplines working together within the arts. So, for example, you will have Kathak dancers having the same vocabulary of expression as a musician. So they will have these spoken patterns, for example, that will be based on time cycles. I mean, I was talking about 7/8 pattern there. Mm-hmm. A time cycle within Indian classical music could be a 10/4 pattern, which in India would be clapped out like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you keep this going. And then within that, you have mathematical structures. So you might have what's known as a tihai that actually explains in an oral tradition how to play the percussion. So one pattern or one phrase might be da-da-ga-da-ga-da-da-da. And if you say that 3 times, it has to land on the first beat of the next cycle. So da-da-ga-da-ga-da-ga-da-da, da-da-ga-da-ga-da-ga-da, da-da-ga-da-ga-da-ga-da. So it lands on the first beat, and it gets more and more complex. Mm-hmm. And it can be extraordinarily difficult. And sometimes dancers and tabla players will be able to improvise, well, they should be able to, within those rules. So rules are very important, within Indian classical music as well as Western classical music. And I think all these different traditions of music around the world have kind of really evolved around constraints that I think really define their identity.
Mm-hmm. Yeah, it's so interesting, this sort of interplay between constraints and what can happen in the presence of them.
Yeah, absolutely. I mean, the mathematics that generated that, as well. I mean, is going to be that's interesting. But ultimately, what comes out is something playful and that feels like a very creative kind of product at the end of it, which is great. And so, what drew you originally to science?
I guess I was really just driven by the questions. Right. I found, the possibility to think about what is the universe made of, how did it evolve, how did we get from the earliest moments to being here today. To me, those were the most compelling questions.
Trivial questions.
Yeah, really small questions. And I've been really lucky to be, this field has just been in this flourishing renaissance. It's so data rich for the last 20 years, and I think we're almost guaranteed to have a similarly exciting 20 years. We went from, when I started graduate school, we didn't know these basic questions: how much matter is there in the universe? And that's something that we now have measured very precisely. So when I was talking about the age of the universe, we talked about this. The age of the universe, we now know it's about 13.8 billion years with an error bar of 20 million years. So Nitin said earlier...
I was 10 years out of date because I said 13.7 billion.
Yeah, so 13.7 is close enough, but actually our measurements are so precise that we can actually say that it's not 13.7, it's 13.8. So to me, that's really amazing.
And that's in the last 10 years you've discovered.
That's just absolutely. And so it's this really interesting thing where we're measuring very precisely these numbers that tell you what is the universe made of, how did it evolve on large scales, and we have a theory that essentially explains everything that happens on the universe on large enough scales, like much larger than the scale of a galaxy. But there's lots of scales that matter, and so once you get down to smaller scales, other kinds of physics matters more and more, and you start to care about how do stars form, what happens when black holes eject energy into their surroundings, how does that impact the gas, what happens when these stars impact the gas, and all of those are really complicated computationally and also challenging to observe. But, we're making good progress, so,
It's very exciting. I mean, I get very excited as well seeing all this. I mean, in my kind of very crappy kind of amateurish way, I read The New Scientist every week, and I've been amazed by the photograph of the black hole emerging, and then also the Fracking-Renner experiment with quantum physics, just kind of recalibrating how we perceive everything, and it's just so exciting seeing how quickly our perception of everything can shift. It must be difficult to keep up. I mean, how do you keep up with everything?
Yeah, I mean, it is. I feel really lucky to be in this field where your mind is kind of blown all the time. I mean, it was, really incredible I think, for everyone to see this picture of a black hole, and we really are discovering things at such an amazing rate. I mean, the fact that we've now, seen thousands of planets outside the solar system, that's all essentially within the last 10 years. So it's really incredible, I think. And one of the amazing things is, how all of these different scales are connected. So, maybe we can go on to the next movie. And the next movie that we're going to see is, as I mentioned, it's essentially the evolution of a piece of the universe that we're watching almost the whole history of the universe, starting about 500 million years after the Big Bang until today. And the interesting thing is what goes into this is the seeds of structure that actually came from quantum fluctuations in the very early universe. In the first tiny fraction of a second, the universe expanded really, really rapidly, and the quantum fluctuations basically became real and created the matter that we see. And so that's what we're going to watch here. This movie is actually just gravity. But you'll see something about where the galaxies form. So let's go ahead and watch this.
Great. That's an amazing visualization. I have to say that one was very emotional when I first watched it. I think there was something really touching and profound, and maybe it's because it's kind of it's black and white, and then you have these incredible lights, and then when you realize that each light is a galaxy, it's a very profound realization. And there's something about it that kind of I think underlines how small we are, really. And you feel kind of in awe watching it. I think I did when I first saw it, particularly again 3D, but it just really felt very immersive and experience to see.
Yeah, I love this movie. I've watched it probably hundreds of times, and this is the kind of simulation that my group does, but I can never get tired of it. And I also really appreciate what the music brings to it. It sort of highlights the power, and there's this sense in the music that I felt like there's this sense of anticipation of, like, one of the things that's interesting in this movie, if you look at it carefully, as Nitin said, you know, the black strands, that's the dark matter in the universe. The only thing that's in this movie is essentially what are those initial conditions that come from the quantum fluctuations, basically what are the constituents, how much dark matter, how much normal matter, how clumpy is the early universe, and then gravity. So that's the only physics that's in there, is gravity. But one of the beautiful things here is that gravity works really on a very broad range of scales. So what's interesting, if you pay close attention to the movie, you can see that in some regions, there's like a lot of stuff happening. There's galaxies colliding, there's, you know, matter being brought in and drawn into the galaxies, and galaxies lighting up. So in this movie, the galaxies are a model. So in our understanding of galaxy formation, galaxies form in regions where you have enough dark matter in one place, and you have enough dark matter in one place that you start to cool the gas and start to form stars, and that's where you get a galaxy. We think every galaxy forms in this way, surrounded by a much larger amount of matter. And it forms, you know, sort of from small to big. So, you know, in the beginning, there were just these tiny little spots, and then eventually those merge and grow to become big galaxies like the Milky Way today. And what I love that somehow for me, watching it this time, the music brought this sense of scale somehow to me, that there are these sort of, there's quiet on large scales, but then action on small scales.
Wow, well, that's great. What I was going to, one thing that you mentioned earlier when we were chatting was that that dark matter is 85% of all matter in the universe, and I was struck by that because it combined with the fact that 100,000th of the diameter of an atom is its nucleus, where most of its mass is concentrated. So I was thinking, God, there's just, you know, it's incredible how we have this perception of reality as this all-encompassing thing. Reality as we know it, everything we can see, feel, touch, and yet it's interesting as well to me that both Einstein and, I mentioned before, Rabindranath Tagore, when they were talking all those years ago in Berlin, they both came to the conclusion independently that the universe was an illusion, which I found quite fascinating. And in one way, I think it possibly was a convenient abdication of responsibility for their lives, which were quite interesting, their lives. But I kind of think that it's also, years ago I went to interview, I imagine a lot of you here may know who David Deutsch is, and I went to interview him. He's a quantum physicist who was a visiting professor at Oxford University, and I'd read his book, The Fabric of Reality, and I was so interested by his interpretations of Hugh Everett's concepts of the many worlds theory, which he came up with in the 50s. David Deutsch had this concept of the multiverse, and he talked about that in relation to quantum theory, and that the universe split into different possibilities. I think it's also based on double-slit photon experiments, and so I kind of think it kind of fascinated me, all of this, because I think that reality is such a fragile thing to grasp in so many ways, and so quite often I will work with intuition over my logical brain, because I think my logical brain quite often will kind of fool me into thinking certain things. I mean, G. Hardy, the mathematician who worked with Srinivasan Ramanujan, he actually talked about the fact that mathematics was the only reality there was that you could rely on, and that everything else was fallible. So it kind of, there's something about this that kind of makes me feel like our intuition is so much, it's so kind of enmeshed with the way in which the universe, how we perceive the universe. And I guess as a musician, I'm always thinking that way.
Yeah, it's so interesting. I find it's one of the things that I love about the movies is it brings such different things to different people, and it also does just change your perspective on, in my daily research life, I'm working exactly with data from movies like this one, but it's much more abstract. We're looking at the correlation of some objects with some other objects and comparing them to things to the galaxies that we're mapping out in the universe. But what that's all like much more abstract and much more numerical. And so to actually feel more what it looks like, and when you experience it in 3D, and then when it has a soundtrack, it becomes much more visceral. So I really love that about this connection.
I'm glad as well that you said visceral, because for me, it's also, because it could be quite soporific an experience to watch something like this, because it's a very beautiful visualization. But I wanted to bring out the kind of visceral nature of things colliding, and what you said, earlier today when you were talking about how dark matter passes through us all the time, but it doesn't actually, it has no. It has no mass. But
it has mass, but it doesn't interact.
Yeah, it doesn't interact. Sorry, my mistake. But the idea of that it actually is passing through us all the time, and that there are these collisions taking place. Yeah. That was something that I kind of found amazing and really inspiring musically, which is why I put in these kind of crazy beats towards the back end of it to kind of give this backdrop of against all this kind of choral sound and orchestral sound, something that felt quite visceral and had that feeling. But should we maybe open things up to anyone who might want to ask anything?
Yeah, let's go ahead and take questions from the audience.
If anyone's got any, or we can just all go home.
I just wanted to let people know that if you do have a question, you can just push the button on your microphone in front of you.
Michael.
So I'd like to ask you about the the big tonal choices in the two excerpts. So in the second one, it's conventional Western tonality. I mean, it's new music, obviously, but it's conventional Western tonality. It's like Smetana's The Moldau, where the little mountain stream becomes a big river at the end. The first one was really different. And you said 7/8 time, and you're using classical Indian modes rather than Western tonality. Yeah. And it's really distancing. So the second one, somehow it was something that emerges in our universe, and the first one was somewhere else.
Well,
and I wonder if you would comment on A, sure, whether I got it right, and B, whether you consciously made those choices.
Well, first of all, thank you. First of all, I don't think there's a right and wrong. I think it's a subjective experience, as all music would be. But I think, and I appreciate yours, but I think in the first piece, it's interesting because you find it from somewhere else. For me, it's very familiar territory, and both are equally familiar. As I said, I have a background in classical Indian and classical Western music, so I just will allow my intuition to speak to me more than anything. And so, yes, I'm kind of using. I mean, recently I wrote an oratorio, which we actually had performed with the National Youth Orchestra and the London Contemporary Voices at the Barbican. And I kind of find that it's very powerful just to sometimes rely on orchestral sounds and choral sounds just to get across something quite profound and a strong feeling. But then at the same time, I have a very strong connection with Indian classical music, and rags, to explain what a rag is, it literally means color within Indian classical music. So the equivalent would be modal. So you might have the 7 modes, and you have 72 basic rags within Indian classical music, which all have very complex rules associated with them, not just mathematically, but also in terms of the intervals and the use of those intervals. So it's kind of, these were just 2 separate pieces that I kind of looked at in their own right, drawing on my understanding of music from different angles. But if I were to do another 10 pieces, probably each one would sound very different, but it's all coming from a feeling that I would have as a response to whatever I'm watching. I don't know if that helps. Thank you. Okay, cool. Any other?
Yeah, okay.
For the first piece, reionization is also cosmic dawn. Did you actually know that term, or?
Cosmic dawn. So he was saying that the first movie, another name for that time period is cosmic dawn.
Because I felt you were invoking dawn through your music, but I didn't know if that was a conscious choice or.
Well, I'm kind of familiar with. With the ideas behind this, because I'd heard Risa give a talk about them, but I think I also wanted to kind of react more from a visceral perspective. But we were talking about, it was interesting because we were talking about cosmic microwave background radiation, and I find all of it so fascinating because I remember when I was a kid staring at television sets with interference on for ages. Had I known at the time that 10% of that was actual cosmic microwave background radiation, I would have been mind blown. and so I kind of think there is something that I maybe have channeled about that, or the feeling of that. But I think, as I said, I kind of go with my intuition and feeling first, and then find where it takes me.
Another question? Yeah.
Correct me if I'm wrong, but I think your second piece at some point brings in human voice to it.
Yes.
Can you comment on that? That was really, really interesting, I thought.
Okay, yes. So I mean, that's everything you heard on the second piece was me in the studio on my own in front of a computer. So I'm generating orchestra and voices, playing them on a keyboard. To get into it, there's fantastic software now available. I do write regularly for orchestras. I've written extensively for the London Symphony Orchestra, and I've conducted orchestras. But I quite often, because I'm a film composer, sometimes people will ask you to mock up music before you actually go in. With Mowgli, for example, we went in with an 87-piece orchestra at Air Studios, but beforehand I had to mock things up so they sound roughly like they will sound in the final version. So nowadays there's incredible software available. There are companies like Spitfire who will come up with simulations of orchestra. For example, they will spend ages sampling each and every note played by an orchestra at different dynamic levels in order to be able to play based on velocity in the way in which you're playing the orchestra on a keyboard. And in the same way, you can do that with choirs as well. That choir that you heard was coming from software that had been developed by Eric Whittaker, who's a well-known choral arranger. And that was actually his choir that I was playing on the keyboard, effectively. So the chords and the composition are all generated by me, but the sounds have been developed by software engineers.
I was actually asking a slightly different question. What was the relationship of bringing the voice in terms of the evolution of the universe?
Oh, right, okay, sorry. So yeah, that's actually, okay, so the voice, I suppose I put it towards the back end because it felt like, our journey. It's
interesting because it's actually, I think it's actually approximately perfect timing. In that, it came in maybe, I would need to check, but maybe it came in about 4.5 billion years ago.
I doubt it, because actually we weren't around that long.
No.
But I think in terms of that kind of an anthropic feeling. Kind of I wanted to bring that in because actually our perception of time is relative, obviously, and the way in which we look at everything is subjective. So we have perhaps a distorted perspective on how important we are. So maybe I kind of brought in a choir to kind of represent that. I think that's probably what my thinking was at the time, was that I wanted to actually bring in human voices towards the back end of it. Thank you.
Yeah.
So I'm really curious about this notion of frequencies and resonances and sounds and matter in the universe, from the music of the spheres to these recent events where we were able to hear a gravitational wave, right? And it's this awe-inspiring whoop, like that. Yeah. Or that I understand the black hole sounds at 37 octaves below middle C at a B flat. Yeah. So I'm just curious if you two might talk a little bit more about, like, not only using sound as a tool of measurement, but also these notions of scale and how to bring scale from cosmic scale to human scale, and the kind of role intuition may play in talking about that multiverse of scales from cosmic to human.
I mean, as you said, Pythagoras and Johannes Kepler talked about this in relation to, Kepler talked about it in terms of the average distance of the Earth from the Sun being a semitone, and he talked about mi far, in relation to that. So you're right, there is this kind of idea, but also I guess, sorry, something came to mind as you were saying that I was just going to elaborate on. I think that it's important to kind of look at how sound has kind of, how we've all perceived sound historically over time, and how it's evolved. I mean, recently in 2018, in August, they've now discovered, or they're now talking about sound waves actually having negative mass, which amazed me. So actually sound travels up, which I was astounded to hear. But it's kind of, I had no idea of that. I mean, it's an incredible concept to me. And so there are constantly discoveries that kind of make me question the nature of sound and so on. I mean, Tesla, obviously, in terms of harmonic resonance and what he could do with it and the power of it, again, it makes you think about low frequencies and how you use them, and how powerful and emotional they can make you feel. For example, even thinking about music from the perspective of how animals perceive sound. Animals perceive sound for communication, survival, reproduction. We actually imagine that we are unique in that we derive pleasure from music that's different to animals. But actually, there's experiments which show that chimpanzees have oscillatory phase lock. That means that they are bothered by dissonance within music. So dissonant intervals, ratios that actually are uncomfortable to them, make them agitated. And so conversely, consonant intervals will make them feel, pleasure in the same way we get pleasure. So there's quite a lot of research in zoomusicology that indicates that that the way in which we perceive sound is not just unique to humans, but also it's within the animal kingdom, but also through people like Kepler and Pythagoras and Galileo's father. There's all kinds of research that was done a long time ago that indicated that it's fundamental to how how the universe has evolved.
So I'll just pick up on a couple of those topics, and then we'll end. I think it is really interesting, one, how sound actually is a tool for understanding the universe, and the gravitational wave is a great example that gravitational waves are not really sound waves. But they are something which has a frequency which can be turned into sound waves and actually help us understand, as we said, like viscerally, like this helps us in some way understand, that whoop, which is actually, those black holes going faster and faster together. It really is a frequency. So I think that's a really cool way of like taking something that might be less visceral and making us sort of understand what it is. I think another thing that comes to mind that was sort of part of your question is actually how we use sound waves to learn about the universe. There's a really very cool thing about sound waves in the early universe that actually, as the normal matter is interacting with photons, it leaves this sound wave in the early universe that actually leaves an imprint on the distribution of galaxies. It goes by a funny name called baryon acoustic oscillations. And it really is based on sound waves in that early part of the universe. And that is actually going to be, over the next few years, one of our amazing tools using the spectroscopic survey we were talking about called DESI to actually figure out what the universe is made of and how dark energy is evolving. It's actually using the imprint of those early sound waves. So it's very cool. So I think we're going to have to stop. I want to mention that actually, maybe I'll just call on Laura.
This? Ooh. Hi, my name's Laura Evans from Stanford Live, and I would like to tell you about the concert we are having on, well, we have two concerts featuring Nitin Sawhney. On Friday night, he's collaborating with the Stanford Symphony Orchestra in some of his original compositions. It will be really very nice. And then on Saturday, we have a program called Music in Motion, also at Bing Concert Hall at 7:30, and it's a showcase of artists thinking about art and technology. These films will be shown, and Nitin will be in conversation with Ge Wang, a professor up at Karma. And we're also featuring Kaki King, who is a guitarist who does things with visuals projected onto her stationary white guitar, and her playing generates the imagery. She's very interested in data visualization. And then we will have a piece called Alternating Currents, which features a dancer interacting with a Tesla coil. So please come, it will be a wonderful event.
So thank you all for joining us today, and I hope that you'll stay there's a reception just outside the auditorium. Thank you so much.
Thank you. Yeah, pleasure. It was really fun.